What the heck? Hey, listen, deep learning! Deep learning! Machine learning! Are we ready for machine learning? We're going deep, 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 deep in the machine. Who's ready? Today! Who's ready? We are going deep in the learning of the machine. Today, we are the neural network. We are the programmer with the power of the machine. Say, here we go. Radio. Who's ready? Play that song for me. Come on, who's ready to go deep in machine learning? Today is the day. Woo! Woo! Today is the day. What's going on? Hope everybody's having a good day today. Woo! Feels good. We are ready to go. We are ready to go. We're locked in. We are wired in. Where's Mark? He's locked in. I need to speak to Mark now. He's wired in. We are wired in. We are Mark. We are summoning the power of the Zuckerberg. Today, listen up. All attention. All rise. We are going deep with MIT OpenCourseWare, solidifying our reading knowledge of deep learning. Today should be a fun one. What's going on, everybody? I'm excited to be here. I'm feeling good. I'm hyped, as you guys can tell. This should be a fun one. I have been pondering. I have been getting cracked, as they would say. We have been becoming cracked, as they would say. We are learning deep learning. We are going deep. We are doing what we can to better ourselves and push our programming to the next level. Welcome. This should be a good one. So if you guys aren't familiar, we have started learning deep learning. A couple days ago, we started off with reading deep learning with Python. It's a great book so far. We started reading chapter 1 and we slowly worked our way through chapter 2. I will preface, chapter 2 is pretty dense. There is a lot going on there. It goes over a lot about neural networks, about backpropagation, forward propagation. It goes over about layers. It goes over about, it goes over about matrix transformations. It goes over about, learning. It goes over about, all the stuff. Actually, implementing code. It's a huge chunk of a chapter, right? I walked away from there. We took a shot. I've been hit. I've been hit. I've been hit. But hey, we went back to the lab. We went back to the lab. We made our way back. Yeah, we got home. We thought. We let that marinate. We let that information sit. We watched 3 blue, 1 brown. Whatever. 3 brown, 1 blue. Brown is brown, 1 blue is brew. We watched a guy I posted in the Discord. We solidified the knowledge. We got visuals of gradient descent, stochastic gradient descent. Today, we are going to solidify this knowledge further, right? I want to really hammer this home. This stuff is deep learning. This is hard stuff, right? We don't want to brush over this. We want to make sure these fundamentals are sharp. Yes, we read chapter 1. Yes, we read chapter 2. Yes, we did watch alternative videos, 3 blue, 1 brown, and whatever this guy was. Hold on. Pause. 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 Artem Krishnov. This guy. GOAT video. Such a cool video. We watched him.
And that reason
it was sweet. And we are back. We're going to solidify the knowledge up today by reviewing, hopefully, a lot of this should be reviewed now. We have learned the core basics of what a neural network is, how it works, what are the steps throughout it. Now we're going to solidify that knowledge and hopefully have an open discussion here with the professor as we watch this lecture together. This is lecture 1 of MIT's 15.773 Hands-on Deep Learning, spring of 2024. Introduction to Neural Networks and Deep Learning, Training Deep NNs. Pause. All right, you guys. I've tried my best to keep the hype here and get everybody excited. So it's now your turn to engage with the material with me here. Let's go. What's up, Panda? How's it going? Hey, Kyle, what's going on? Pre-game ritual, hey, sappy treat. When you finish the course, I expect a full neural network created in C. Well, that's my goal, is I really want to write a neural network from scratch in Python and then eventually work and migrate it into C with our learning and, solidify our mastery and learning in C that we've been doing so far. Even a machine learner had a hard time considering how hard deep learning is. Nice. Here we go.
All right, so today's lecture.
Oh, hold up, sorry. Hold up, sorry. Hold on, let me start recording. All right, we are starting. 15773 Spring 2024 Hands-on Deep Learning from MIT. Introduction to Neural Networks and Deep Learning. Training Deep Neural Networks. This is going to be a good lecture series to watch together. Hope you enjoyed. You guys want to watch live with me on the stream? I stream almost every single day. Teach myself computer science programming from the ground up. Thank you so much for being here. Let's go ahead and get into this.
All right, so today's lecture, Introduction to Neural Networks and Deep Learning. So we'll start with a very quick intro to these things, and then we'll switch and dive deep into neural networks. All right, so the field of AI originated in 1956. Sadly, it didn't originate at MIT, it originated at Dartmouth, because all these people got together at Dartmouth. I guess it's got a nice quad or whatever. They got together, they defined the field.
Got a nice quad or whatever.
Fortunately for us, MIT is very well represented. So
we're starting off high. I like this guy.
Who founded the MIT AI lab, John McCarthy, who invented Lisp, and then later defected to the West Coast, and then Claude
Let me know how the audio is. If you guys want me to turn it up or turn it down, let me know, please.
So MIT was well represented. These folks, founded the field, and they were so bright they thought that AI was going to be substantially solved, quote unquote, by that fall. Okay? Now, obviously, it turned out a bit differently than what they expected. So it's been, whatever, 67, 68 years since its founding. So it's gone through, essentially, in my opinion, 3 seminal breakthroughs, starting with the traditional approach, then machine learning, deep learning, and generative AI. So let's take a very quick look at each of these breakthroughs and what motivated them.
Let's see.
So let's start with the traditional approach to AI. And so what is AI? AI informally is the ability to imbue computers with the...
Okay. You? Absolutely.
Dude, I don't know why. Why? It's so annoying because it should not be doing that alert sound anymore. I thought I turned that off. What the heck? Hold up, you guys, sorry. I thought I turned that off. Come on. Alerts. Yeah, I turned off the audio file. Can I just delete it altogether? Hold up, guys, sorry. How do I just turn off the alerts? How to turn off alerts, stream labs. How to turn off these alerts. I deleted them from the source, so I don't know why they're still playing in my... Maybe because they're in my vertical scenes? Hold on. Hold up. Vertical sources. Delete. Delete. Okay. I think that's all of them. So it should be no longer doing those. Hey, War, what's going? Hey, what's going on, Dev Larry? Welcome in. All right, you guys ready? All right, I think we're good. Okay, sorry about that. Appreciate all the subs, though. Thank you guys so much. We've been really getting a lot of subs lately. We're almost at 7,000 subscribers. Almost getting like 2K in like 1 week, which is crazy. You guys are nuts. Thank you guys so much for all the support. It seems like everybody liking the deep learning and the more like advanced stuff. So appreciate you guys being here. We're gonna keep going. And yeah, welcome in. Here we go. Oh, hold up. Always something, right? Always something. OBS has a lot of glitches.
That only humans can. So breakthroughs, starting with the traditional approach, then machine learning, deep learning, and generative AI. So let's take a very quick look at each of these breakthroughs and what motivated them. So let's start with the traditional approach to AI. And so what is AI? AI informally is the ability to imbue computers with the ability to do things that only humans can typically do, cognitive tasks, thinking tasks, and things like that. And so the most sort of commonsensical way to do that is to say, well, if I want the computer to do something complicated like play chess, I'm just going to sit down with a few chess grandmasters show them a whole bunch of board moves, and ask them how they figure out how to respond, how to play the next move. I'm going to sort of sit down and talk to all these people, and then I'm going to write down a whole bunch of rules. If this is the board position, move this. If this is the board position, move this, and so on and so forth.
Synthetic AI, right? We talked about that.
And tell them, okay, how do you actually interpret an ECG? They will give me all the similarly
kind of outlining all of the rules.
All these rules, I'll put them
pretty
in the computer,
robust.
and boom, I have a system that can
pretty
do what a human can.
fragile to
right?
change,
now,
to implementation
this approach,
of new
even though it's commonsensical
angles,
and
new
kind of makes
perspectives.
sense, it had success in only a few areas. And so the interesting question is, why was it not pervasively successful? Why was it not pervasively successful? It seems like a pretty good idea to me.
Right. New
and the people who
inputs
came up with these things are smart people. They
require
dumb
drastic
people.
changes
They know what
and
they're doing.
reflection
So
across
why did
all
it
of the
not
already existing rules. It's pretty hard
Because
to implement.
Because it's time intensive, so in case like you have to run through all these scenarios that can ever exist, and still some new scenarios can come up that you didn't cater for initially.
Right. So there are two aspects to what you said, which is the first aspect is it's time intensive. That, as it turns out, is not a big deal
Not a
because
big
computers
deal.
are getting faster and faster.
Yeah, computers are fast,
Right?
so
The
it's not as much
second
as
thing is
a
actually the
time
key
thing.
which is that it doesn't generalize to new situations very well. Right? The problem is there are an infinite number of things that you're going to see when you deploy these systems in the real world. By definition, what you're training it on is a small sample of rules. So these rules are very brittle. But there's actually an even more interesting reason. And that reason is that we know more than we can tell. This is called Polanyi's paradox. So the idea is that if I come to you and say, hey, here's a picture. Is it a dog or a cat? You will tell me within, I believe they've measured it like 20 milliseconds or something. You know if it's a dog or a cat. And then if I ask you to explain to me exactly how you figure that out, you'll come up with a bunch of sort of reasons, right? Alleged reasons. Oh, if it has whiskers, I think it's a cat or whatever. Mm-hmm. But the problem is that you actually, first of all, can't really articulate what's going on in your head, how you do these things. And number two, even if you articulate it, oftentimes your articulation has no correspondence with how your brain actually does it.
Yeah.
So you're incomplete and a liar. So this is Polanyi's paradox. So if you can't even tell me how you do something, how the heck am I supposed to take it and put it into a computer? It doesn't work. And second is the fact that we can't write down these rules for all possible situations. Edge case.
All right, so we have this Polanyi's principle. So like, why is this so difficult? Right? It's so difficult because we know more than we can tell, right? We can't articulate that well all of the rules for all of the scenarios in which we do things, right? Yeah, we might be able to describe a few things, but oftentimes might not even be really describing the way that our brain is actually, doing those interpretations on its own, right? So it's kind of interesting how even so the communication about the rules, if we were to try to make a rule-based traditional or synthetic AI system here, is that we will not even really be conveying accurate information how our brain is actually working about optimizing, what are these images, what are these this, what is X, what is Y, right? So we have, quote, we know more than we can tell, right? Which is really interesting. This is Polanyi's paradox. We can do a lot of things easily, but find it very hard to describe exactly how we do them. We can do of things easily, but find it very hard to describe how exactly we do them. And then we can't write down if-then rules to cover all situations and edge cases. Yep. Can't write down if-then rules to cover all situations, edge cases, etc. We can't generalize new situations, right? Perfect. We hit that one on the head. Nice. Everybody seems to be getting this. Make sure, if you guys want to engage with it, use the chat. Answer the questions he's given here. It helps with your learning too. Not only just listening to me, but spitting it out yourself. and have it learn about, okay, given input, what is the potential output? How do we get there? Yep, we learned about that. Okay. Yeah. Like a statistical data set about some population sample. Yeah. Booleans, yes. Yes, true, 0, 1. Puppy no more, dog no more. Oh my god. Red, green, blue, RGB pixels. Yep. Luminosity. Some combination of RGB creates, a whole color spectrum that we can make pictures with individual pixels. Think about it like Minecraft, right? Zooming out on pixel art, you can make whole pictures with individual pixels. Now that's just kind of like one individual color, right? But imagine kind of taking a chunk of 3 different blocks and then using that in components to create your pixels. That'd be a cool project. Mm. We have many representations as we go through our layers in our networks and stuff. Oh no. Why is this video? Are you serious? Why is this freezing? What is going on? Like, why is OBS so trash? Come on, dude. That's so annoying. I'm sorry, you guys. Ugh. Really have to go back and watch all that crap? That's so troll. I'm really sorry, you guys. Okay.
Come to you and say, hey.
All right, so I think we're back here at this part. So annoying.
Tell. This is called Polanyi's paradox. So the idea is that if I come to you and say, hey, here's a picture. Is it a dog or a cat? You will tell me within, I believe they've measured it like 20 milliseconds or something. You know if it's a dog or a cat. And then if I ask you to explain to me exactly how you figured that out, you'll come up with a bunch of sort of reasons, right? Alleged reasons. Oh, you know, if it has whiskers, I think it's a cat or whatever. But the problem is that you actually, first of all, can't really articulate what's going on in your head, how you do these things. And number two, even if you articulate it, oftentimes your articulation has no correspondence with how your brain actually does it. So you're incomplete and a liar. So this is Polanyi's paradox. So if you can't even tell me how you do something, how the heck am I supposed to take it and put it into a computer? Doesn't work. And second is the fact that we can't write down these rules for all possible situations. Yeah. Edge cases, corner cases, etc. And the world is full of edge cases. So for these reasons, this approach didn't work. And so a different approach was developed. And this approach was, well, basically said, hey, instead of explicitly telling the computer what to do, why don't we simply give it lots of examples of inputs and outputs, chess positions, next move, right? ECG diagnosis, right? Inputs and outputs. And then why don't we just use some statistical techniques to learn a mapping, a function that can go from the input to the output. Okay, that was the idea. And this idea is machine learning. Okay, so machine learning is basically just a fancy way of saying learn from input-output examples using statistical techniques. Good. All right.
Learn from input-output examples using statistical techniques, right? Okay. Cool. We're still now we're getting.
So. Now, there are numerous ways to create machine learning models. And if you have ever done linear regression, congratulations, you've been doing machine learning.
Okay, so there's numerous ways to do machine learning, right? We have a bunch of different models of like machine learning, like different mathematical techniques. Neural networks is just one of them. It's kind of more of like a popular pop sci culture one, though, right? You know, so we have numerous ways to create machine learning models. Right? So we have things like linear regression. We have logistic regression, classification and regression trees, support vector machines, random forests, gradient boosted machines, and the neural networks, and then etc., right? And many more. Cool. Right, okay. Yeah. We've gone over that before. Okay, why did it do it again? What? Why is it doing this? Ugh. Stop it. Like, OBS sucks, dude. Why does it keep doing this? Let me see if I can just do... I'm doing a display capture on this whole display. Now stop. So frustrating.
Models, and if you have ever done linear regression, congratulations, you've been doing machine learning. Okay? And only one of those methods happens to be something called neural networks. There are many other methods. And in fact, you probably have done these other methods if you have done a course like the Analytics Edge or something similar. Okay, so machine learning has got tremendous impact around the world, right? It's like, at this point, it's widely accepted that it's a very, very successful technology. And in fact, whenever people are actually talking about AI, chances are they're actually talking about machine learning. It's just that AI sounds cooler.
Yeah, it's just kind of like...
The only problem is, for machine learning to work really well, the input data has to be structured. Okay? And what I mean by that is data that can essentially be sort of numericalized and stuck into the columns and rows of a spreadsheet. Right? So for example, here, let's say I want to put together a data set of patients, their symptoms and their characteristics, and then in the following year after they showed up at the doctor's office, whether they had a cardiac event or not. I might create a data set like this with age, smoking status, yes, no, exercise, blah, 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 right? And so either these numbers are numbers, they're numerical, or if they're not numerical, they're categorical, right? Yes, no, smoking, yes, no, things like that, which means that if you have categorical variables, you can just numericalize them pretty easily. You folks have done some machine learning before, so you know things like one-hot encoding and stuff like that can be done to make them all numerical. So the point is, you can just render the data into the columns and rows of a spreadsheet pretty easily, right?
Yeah.
That's what I mean by structured data. So but the situation is very different if you have unstructured data. So if you have an image of, a cute puppy, this is my puppy, by the way, from many years ago.
I've seen this like 4 times. We had to go back so many times.
But his name was Google. So yeah, anyway, my DMD alums know Google well. So this is Google, right? If you want to take Google, this picture, and figure out how to sort of numericalize it, the first thing you need to understand is that if you actually look at how this picture is represented inside digitally in the computer, basically every picture like this is represented using 3 tables of numbers. Okay? And we'll get to what these numbers mean later on, but the point I'm making is that each number basically represents the amount of light. Right? On a scale of 0 to 255, the amount of light in that location, in that pixel. That's all, the amount of light. So basically, this table is the amount of, this table is the amount of red light, amount of green light, amount of blue light. Okay? Now, you will agree with me that if you, for example, look at something like this and say, okay, 251,
Yo, like, what is going on? I'm gonna create like a new scene. Like, I didn't even do anything. And it just stopped. Like, it just froze. Like, this is so annoying. Mac OS screen capture. Delete this piece of crap.
Agree with me that if you, for example, look at something like this and say, okay, 251 at this location, there is a lot of blue light because it's 251 out of a possible 255, right? Maybe a lot of blue light somewhere here. There's a lot of blue here. Whether that area is blue because of a piece of sky, some water, or a bunch of blue paint, could be anything, it's going to say 251. So the underlying reality, the underlying object that's being described has nothing to do with the 251, right? So that's the whole problem. The raw form of the data has no intrinsic meaning with the underlying thing. So given that there's no connection between the number and what it's describing, how the heck can any algorithm do anything with it? It can't.
If you're confused on what he meant by that, he's saying, okay, so if we have an image, like he said in this case of his dog, right, and we have a single pixel on this screen, and it's displaying 251 for some shade of blue, right? Well, that's just a shade of blue. We don't know the context behind that shade of blue. How can we tell? Like, is that blue belong to some water? Is it someone's blue eye? Is it my hat? Is it his shirt? Like, it doesn't, necessarily, like, it doesn't, there's no context behind what that singular data point has. So that's where I think he's going to maybe get into lines of how it input outputs, and it will, based on certain weight biases on certain edges between these layers, right, that we've learned about, we can, certain weights pull certain to desired outcomes. We can learn what that blue should mean in certain contexts or something like that, maybe.
Right? So what you have to do is something called feature engineering or feature extraction, right? Where you have to manually take all these things and create essentially a spreadsheet from them. So basically, let's say that you have a bunch of birds, right? And you're trying to build a bird classifier to figure out what kind of bird species it is. You might actually have to take this picture, and then you have to measure the beak length, the wingspan, the primary color, and so on and so forth. So you're basically structuring the unstructured data manually, right? And this process of structuring unstructured data is basically called, we use the word representation. We take the raw data and we represent the data in a different form. And the reason why I'm sort of focusing on the use of the word representation is because it becomes really, really important a bit later on when we get to deep learning. Okay?
Right.
So we have to represent the data in a different way for it to work. That's the basic idea. All right. So what that means is that historically, researchers would manually develop these representations. And once you develop them, once you representations, you can just use traditional linear regression or logistic regression and get the job done. So the whole name of the game is the representations. So in fact, people doing PhDs, for example, in computer vision would spend like 4 years developing amazing representations for solving one particular little problem, right? We have a bunch of, say, CAT scans, and we need to take the CAT scan and figure out whether a particular kind of stroke, there is evidence for it in the CAT scan, right? They might actually sit and develop all kinds of representations and test it and so on. And then they'll finally declare victory and say, yay, I'm done with my PhD. Here is this amazing representation. And you can build a classifier with it to predict a particular kind of stroke with high accuracy. Okay?
Oh, that's interesting.
So that's where the world was. Now, as you can imagine, developing representations, because it's so manual, is this massive human bottleneck. And this sharply limited the reach and applicability of machine learning, as you would expect. To address this problem, a different approach came about, and that's deep learning. So deep learning sits inside machine learning. Okay?
To address this problem, a different approach was developed of deep learning. What was the problem again exactly? But developing good representations, right? Developing good representations, before machine learning could be used requires massive human effort. And this, quote, human bottleneck sharply limited the reach of machine learning. Right? So developing good representations, right, required a lot of people's full PhD programs were completely focused on finding representations for some niche, image in some niche field of science, right, like MRIs or whatever. So that's interesting. For those that are in a higher level educations, what have you guys experienced with this? Do you guys have peers or know of anybody that kind of has done these kinds of things with higher level CS degrees? It's really interesting. Right, so that's the bottleneck, is you have to spend a lot of time figuring out, okay, what representation best accurately represents this sort of input, and then gives us the best output, right? Yeah, see, it lags when I do this for some reason. I guess I will change browsers, I guess. Just open up this guy. Yeah, it's a piece of crap.
Developing representations, because it's so manual, is this massive human bottleneck, and this sharply limited the reach and applicability of machine learning, as you would expect. To address this problem, a different approach came about, and that's deep learning. So deep learning sits inside machine learning, okay? And deep learning can handle unstructured input.
So deep learning can handle unstructured input with data without upfront manual pre-processing. Okay. So now we're getting into the deep learning segment here. Right, where deep learning can handle unstructured input data without upfront manual pre-processing.
Put data without upfront manual processing, meaning it will automatically learn the right representations from the raw input. Automatically is the keyword. Automatically learn representations, which means that you could give it structured data, you can give it pictures, you can give it text, you can give it anything you want, it'll just learn it. Okay? It can automatically extract these representations, and since it's being automatically extracted, you can imagine sort of a pipeline where the raw data comes in, you have a bunch of stuff in the middle that's learning these representations automatically without your help, and then boom, you just attach a little linear regression or logistic regression at the end, problem solved. That in a nutshell is deep learning. Input, a whole bunch of representations being learned, and then piped into a linear or logistic regression model. Okay? So the amazing thing is this simple idea is just incredibly powerful, right? That idea has led to ChatGPT, has led to AlphaGo, AlphaFold, and so on and so forth. And I kid you not, I've been doing deep learning for about 10 years now, and every time I look at it, I literally get goosebumps every so often. That something so simple could be so powerful, right? It's really like boggles the mind. I'm like, I'm just so
like this
lucky
guy
to
a
be
lot.
alive and working during this period. Okay? And coming from people who have been in the industry a long time, this sort of breathless exclamation is not very rare, particularly because I'm not in marketing. Okay? I actually mean it. With all due apologies to various marketing folks. So just realized it's being taped. So, okay. So this demolished the human bottleneck for using machine learning with unstructured data. And so it comes from the confluence of three forces, new algorithmic ideas, a lot.
Six, seven subs. What did he ask? I don't remember. What did he ask? Let's go back. Dude. Like, I can't pause. I can't pause the thing. Like, we're only 13 minutes in. This is gonna take forever if I can't pause. Let me see here. OBS freeze on video pause. So stupid. How far did it pause? How far did I have to go back? We've learned about unstructured and structured data like 6 times now.
Automatically extracted, you
trying
can
to
imagine
record it,
sort of a
that's-
pipeline where the raw
I'm trying to record it. That's why it's annoying. I'm trying to make sure it's good for the video, but like this is so ridiculous. We're already 40 minutes on the stream. Like we could have been done almost with like.
data comes in, you have a bunch of stuff in the middle that's learning these representations automatically without your help,
I just can't
and then
pause
boom,
it.
you just
I just have to
attach
go
a
back.
little linear regression or logistic regression at the end, problem solved. That in a nutshell is deep learning. Input, a whole bunch of representations being learned, and then piped into a linear or logistic regression model. Okay? So the amazing thing is this simple idea is just incredibly powerful, right? That idea has led to ChatGPT, has led to AlphaGo, AlphaFold, and so on and so forth. And I kid you not, I've been doing deep learning for about 10 years now, and every time I look at it, I literally get goosebumps every so often. That something so simple could be so powerful, right? It's really like boggles the mind. I'm just so lucky to be alive and working during this period. Okay? And coming from people who have been in the industry a long time, this sort of breathless exclamation
Someone's
is not very
lucky to be
rare,
working.
particularly because I'm not in
Someone's
marketing.
working in this industry.
Okay? I actually mean it. With all due apologies to various marketing folks. So just realized it's being taped. So, okay. So this demolished the human bottleneck for using machine learning with unstructured data.
Yeah.
And so it comes from the confluence of three forces, new algorithmic ideas, a lot of data, and then very importantly, the fact that we have access to parallel computing hardware in the form of these things called GPUs, graphics processing units. And these three forces came together, and they were applied to an old idea called neural networks, and that's basically deep learning. And I'll go through it very quickly because obviously we're going to spend half the semester looking into this thing in detail. So what's the immediate application of the ability to automatically handle unstructured data? What is like the no-brainer application?
Immediate application of handling unstructured raw data. just people's...
It's okay if it's obvious. Tell me.
Like obviously it was text, was wasn't the
Sorry?
application of deep learning.
Image classification.
Right. So image classification, yes. So you can take an image, a good example of unstructured data. You can do some classification on it. But more generally, what I'm getting at is that every sensor in the world can be given the ability to detect, recognize, and classify what it's sensing. Every sensor. Because remember, what does a sensor do? A sensor is just a receptacle for unstructured data. A camera is a receptacle for unstructured video or unstructured, still images. Microphone, unstructured audio, right? So every sensor, you can imagine taking a sensor and sticking a little deep learning system behind it. And now suddenly, what comes out of this center of the deep learning system, you can count, you can classify, you can detect, you can do all kinds of stuff.
Interesting.
In
So,
short,
like,
you can
any,
analyze.
any sensor.
And you can predict, right? And
Is that where we're
this
going?
is the way I'm describing it, right?
No one raised their hand, right? Oh my god. Okay, so it's literally just freezing for like no reason. Like it's not even, it's not my OBS, it might be my dog? I don't know. Maybe this stupid freaking dog. Because it's freezing my whole, it's freezing the entire capture. Really annoying.
Phrased me, okay? In short, the deep learning system, you can count, you can classify, you can detect, you can do all kinds of stuff. In short, you can analyze and you can predict, right? And this is the way I'm describing it right now. You'll be like, yeah, duh, obviously. But you know what? This obviously thing is actually not at all obvious in terms of whether it'll help you find interesting applications or not, okay? So here's something I literally saw last week, okay? Actually, I have another slide before that, but we are coming to that. So, for instance, every time you use Face ID to unlock your phone, this is the basic principle at work, right? The camera and the iPhone is the sensor, and they stuck a deep learning system behind it to do image classification, right? Drama, non-drama, right? That's what it's classifying. And so here, right, you have a breast cancer, it's a breast cancer detection system from a mammogram. By the way, this picture, it's a very interesting picture. So there's a professor in WCS, Regina Barzilai, who's a very well-known expert in this field. And she actually has built a breast cancer detection system, which has been deployed at Mass General Hospital. And it turns out she's actually a breast cancer survivor. And she's good now, all good. But when, after she built her system, I heard that she actually ran that system against the mammograms from many years prior when she went for a mammogram and was told that everything is fine. She ran the system on that mammogram and it came back and said, here's the problem.
No way!
So a very interesting example where a deep learning system picked up something that a radiologist could not, right? So these things can be quite powerful. Obviously, any self-driving system has numerous deep learning algorithms running under the hood. You know, pedestrian detection, stoplight detection, zebra crossing detection, so on and so forth. You know, it's being very heavily used in visual inspection manufacturing. You have various cameras now. So people looking at saying, okay, there is a dent or there is a scratch, they have a little system which is a dent detector, scratch detector, and so on. That's going on right now. And now I come to the example I saw last week, which is, so this is an example of you can create dramatically better products if you really internalize this idea of, okay, it's almost like you're looking at the world and saying, oh, there's a sensor. Can I attach a DL thing behind it? That's the way you should be looking at the world, okay, for startup
Gotta change our
ideas.
mindset here,
so
boys.
Here's an example. Okay, these
Deep
apparently are the
learning,
world's
everything.
first smart binoculars.
Smart
Okay.
binoculars.
This is the binocular.
Oh, it classifies what you're
2 weeks ago.
seeing. That's cool.
where you look at the bird, you look at the bird.
Yeah.
And
Tells you
now
what
it
bird
tells
you're
you what
seeing.
kind of bird it is right there. It's a simple idea, but imagine, right? Imagine you are the first out of the gate with this feature. You will have a little bit of an edge till everybody catches up like 3 months later. Let's be very clear. There are no long-term monopoly windows in the world. There are only short-term windows, so the hunt is always on for a little monopoly window. So here's an example of that, right? So I encourage you to always think about the world as, where are the sensors here? And can I attach something behind the sensor to do something useful with it? Okay? All right. Now let's turn our attention to the output. We have been talking about structured data, unstructured data, and how deep learning has sort of unlocked the ability to work with unstructured data. But you've sort of been neglecting the output side of the equation. So traditionally, we could predict single numbers or a few numbers pretty easily, right? So you've all done the canonical, should this person be given a loan application in machine learning, right? So it just predicts the probability that a borrower will repay a loan based on a whole bunch of data, or supply chain, you predict the demand for a product next week, or you can predict a bunch of numbers. So given a picture, you can say, okay, which one of the
Okay, so it said, well, let me replay it here.
10 kinds of furniture?
It does. Okay, here we go. Yeah, now it paused for some reason. So dumb. I'll just have to make sure I refresh it before I play it again. Okay, so with deep learning, we could predict / generate structured outputs easily, right? So examples, these are just kind of examples. Okay.
Given a picture, you can say, okay, which one of the 10 kinds of furniture is it, right? You can predict 10 numbers, 10 probabilities that add up to 1. You can predict a whole bunch of numbers that don't have to add up to 1, such as the GPS coordinates of an Uber ride. So these are all simple structured output, just a few numbers, right? What we could not do very easily was to actually generate pictures like this. We could not generate unstructured data. We could only consume unstructured data, right? You can generate text, you can generate pictures, and so on, audio, and so on and so forth. So with generative AI, that problem is gone. So generative AI is the ability to actually create unstructured data, all right? And therefore, it sits within deep learning. It still runs on deep learning, but it's just one kind of deep learning, okay? There's plenty of stuff going on in deep learning that's got nothing to do with generative AI. Nowadays, of course, if you're a self-respecting entrepreneur who wants to ride this craze, you'll probably declare whatever you're doing as generative AI, right? And some VCs may actually be ready to fund you. Who knows? But the point is, there's plenty of stuff going on in deep learning that's got nothing to do with generative AI. But this is the overall picture. Now, here, we can produce unstructured outputs, like pictures. You can take this thing, and then you can actually come up with a nice picture description of it. This actually is a very famous picture, by the way, in the world of computer vision. So we are actually going to be analyzing this picture a little later on in the semester. You can obviously go from a very complicated caption to an image. You can go from text to music. Can people hear it? Okay. Yeah. All right. So, and of course, we can go from text to text, i.e. ChatGPT. And then, as of a few months ago, things have gotten even more interesting, where you can actually you can send text and an image in, and you can get text out, right? And in fact, as of a few weeks ago, you can send text, image in an arbitrary sequence into the system, and it will actually come back to you with text and image, right? So things are becoming multimodal. And I just want to share with you like a really fun example I saw recently. So this person sends this picture. Can folks see this? This is very complicated parking sign, apparently in San Francisco. And they're like, it's Wednesday at 4 p.m. Can I park here? Tell me in one line, because you really didn't want GPT-4 to be giving you a big essay about this. Like, you literally want to park. So GPT-4 comes back and says, yes, you can park here for up to 1 hour starting at 4 p.m. And folks, I double-checked this thing. It's correct. We all know these things hallucinate, right? Can you imagine getting a parking ticket and telling the judge, I'm sorry, I didn't realize it was hallucinating? So you have to double-check it. So yeah, so things are getting multimodal very quickly. So the picture here is that within Gen AI, we used to have these separate circles, text to image, text to music, text to this, text to that, so on and so forth. Those are all beginning to merge now. inside Gen AI because multimodal models are going to become the norm this year, right? We already have really good closed models. We actually already have very good open source multimodal models. And so my feeling is that by the end of the year, the idea of using a text-only model is going to be like, really, you do that still? Right? It's going to become like a quaint, old-fashioned thing. I think modality is going to become the norm. So that's where the world is, and this is the landscape. So any questions on the landscape?
What does that look like?
Before we actually start doing some math. Okay. Yeah.
It's not related to the landscape, but it's more related to the breast cancer question. So how did she know that it was evaluating? Like there is a training that you do and there is a testing you do, which is based on the existing breast cancer samples. But he or she was taking the mammograms from past experience, past and also, which is probably a smaller version, which was not there earlier, right? Like I mean.
You mean the evidence of there being a problem would have been smaller?
Yes.
Yeah.
So how do you know your model is trained enough that it can give you correct answers, right?
Yeah. So I think the question is that in general, how do you train your model so that it gives you right answers, given that over the passage of time, the amount of evidence in this data could be very highly variable. So in this particular case of the professor I talked about, everything at that point was going through an expert radiologist. So 5 years ago, this mammogram was seen by a radiologist, and that person concluded there is no problem. So that was the training label, right? The wrong training label. Typically what happens is that training labels could be wrong some small fraction of the time. So you need to have systems that are robust. So your data needs to be complete, it needs to be comprehensive, it needs to have correct labels. If these ideas are not met, your systems are not going to be that good. But as it turns out, with neural networks, even with some amount of noise in the labels, they still do a pretty good job, right? So that's sort of the general idea.
So there has to be some verification at the end.
The verification comes from the human. So remember, when we look at radiology data, the data we're working with is the input is, let's say, an image,
I guess, of it, right?
like a
How do you know it's
mammogram
true?
or something,
Well,
and then a human radiologist
like
or a set of
your
radiologists.
interpretation afterwards, like whether you take the answer and believe it as true or not, like whether we get to models that are 99.999% efficient, that error is so small in magnitude, or if we stay at 97, 98, whatever it is, and there is that 1%, and it does cause with large enough data, law of large numbers, right? You'll have enough a percentage is large enough on big numbers that it could be catastrophic, right? So who knows? Dude, I really hate this. Why is it doing this? Like this edit is going to be so annoying to figure out.
This combination that's being used to train these models. Yeah. Embodiment. So are we going to cover embodiment? So the embodiment here refers to the fact that if you have robots, right? They need to actually operate in the real world. And so robots are an example of what's called embodied intelligence. So unfortunately, due to the constraints of time, we're not going to get into robotics at all. But I will say that a lot of the deep learning stuff you're going to talk about, those are all fundamental building blocks in modern robotic systems. All right. So in summary, X and Y can be anything, and it can be multimodal. Okay? I literally could not have put up this slide maybe 2 years ago. Right? So it's very simple in how it looks, but it's very profound.
It's crazy how
you can
fast
learn
these teachers
a
have to
mapping
be
from
up
anything
to
to
date on
anything at
their,
this point very easily,
like,
as long as you have an update.
Current findings, right?
So now note that all this excitement
So
that we
weird.
see around us
it's
is
such a different
everything
field than anything else.
stems from deep learning. Okay? Everything depends on deep learning. And so if you understand deep learning, a lot of interesting things become possible. So let's get going. All right? So we'll start with the
Okay, this thing is so annoying. It really is so ridiculous. not doing this anymore. 2450.
Now, note that all this excitement that we see around us is everything stems from deep learning. Okay? Everything depends on deep learning. And so, if you understand deep learning, a lot of interesting
It might have been the
things
browser.
become possible.
Whoever said that, good call. Should have listened to that earlier. Okay.
So in summary, X and Y can be anything, and it can be multimodal. Okay? I literally could not have put up this slide maybe 2 years ago. Right? So it's very simple in how it looks, but it's very profound. You can learn a mapping from anything to anything at this point very easily, as long as you have enough data. Okay, so now note that all this excitement that we see around us is everything stems from deep learning. Okay? Everything depends on deep learning. And so if you understand deep learning, a lot of interesting things become possible. So let's get going. All right, so we'll start with the very basics. What's a neural network? Now recall logistic regression from back in the day. So what is logistic regression? You send in a bunch of numbers, a vector of numbers, and you usually get a probability out, right? Between 0 and 1, what is the probability of something or the other? Okay? And so this logistic regression model is also represented in this form, if you will recall. So basically what we do is we take all these numbers, we run it through a linear function, right? We run it through a linear function, you get a number, and then we take that thing and run it through 1 divided by 1 plus e raised to minus that. And that's guaranteed to give you a number between 0 and 1, which can be interpreted as a probability, and that's logistic regression. Okay? And the canonical, loan approvals, things like that, all fall into this sort of convenient bucket. Okay? So this should be super familiar. All right. Now, we're going to actually look at this simple, modest, humble little operation using the lens of a network of mathematical operations. And the reason why we do it will become clear a bit later. So we'll take this very simple example where we have, let's say, 2 variables, GPA and experience. Right? This is the GPA of some graduates, number of years of work experience. And then this is the dependent variable, which is either 0 or 1. And 0 if they don't get called for an interview, 1 if they get called for an interview. Okay? It's a 2 input variable, 1 output variable problem. Okay? And it's a classification problem because we are classifying people into, will they get called for an interview, yes or no?
Yes or no, okay.
Okay? And so that's the setup for this problem. And let's say that we actually run it through we actually try to fit a logistic regression model to it. So if you're familiar with R, for example, you would use something like GLM to fit this model. If you use something like stats models in Python, there's a similar function for it. Scikit-learn, there's another function for it. You get the idea, right? You can use whatever favorite methods you have for logistic regression modeling to get this job done. And if you do that with this little data set, you're going to get these coefficients, right? The 0.4 is the intercept. 0.2 is the coefficient for GPA, 0.5 for experience. And that is a resulting sigmoid function. Okay? All right, cool. So now let's actually rewrite this formula as a network in the following way. So first, what we'll do is we'll take GPA and experience and stick it here on the left side. Okay. And we'll put little circles next to them, and we'll call them the input nodes.
Yep.
Okay? And so imagine that somebody writes a GPA into the circle, 3.5, or years experience, 2.0. And then it flows through this arrow, and as it flows through, it gets multiplied by its coefficient, 0.2. The 0.2 is coming from here. Similarly, experience gets multiplied by 0.5. It comes in here. And this node, as the plus indicates, is adding everything that's coming into it. So it's adding 0.2 times GPA, 0.5 times experience, plus the intercept, which is the green arrow coming from on its own. It comes through here. And what comes out of this is just a single number. And that number goes into this little circle, and then out pops a probability. Okay? So I've sort of done this ridiculously long-winded way of writing a simple function.
Yeah.
Okay? And the reason why I'm doing it will become clear in a second. Okay? So this is a little network of operations for the simple function. And so, for instance, how you would use it is to make a prediction, let's say someone has a 3.8 GPA and 1.2 years of experience. You just plug it in here, do the math, you get 0.76. Same thing here, comes in here, add them all up, you get 1.76. You run 1.76 through the sigmoid, you get 0.85. And that is the probability that that particular individual may get called for an interview.
Yeah.
OK? At this point, we're just doing logistic regression, nothing more complicated. OK, so
we're just applying some weights now on these. Yeah. That sounds good. Multipliers on values from each node, coefficients equals weights. I like this guy. Coefficients, right? And the intercept is the bias. Ah! It's doing it. Why is it? So now you have not two. Dude, I'm sorry, you guys. This is really frustrating. How far back was it? So now you have many variables, not two variables. Oh, here we go.
OK, so now if you have many variables, not two variables, like x1 through xk, you can, the same sort of logic applies. Each one has some coefficient, and then there's an intercept. They all get added up here, run through a sigmoid, and out pops this number. OK? Notice how the data flows from left to right. OK? All right. Any questions on this?
That sounds good.
All right, good. So now terminology. So you'll discover that the world of neural networks and deep learning has its own terminology. They have their own ways of referring to things that the rest of the world has been referring using something else for the longest time. Right? It's kind of annoying sometimes, but it's the way it is. So
Word.
remember in regression, we used to call those numbers next to each variable as coefficients, and the constant thing as an intercept. Well, guess what? In this world, those coefficients are actually called weights.
And the intercept
And
is
the intercepts are
bias.
called biases.
Yeah.
So in the neural network world, these are called weights and biases. And sometimes if you're a little lazy, you may just call the whole thing as weights. OK? So when you see in the newspaper that, oh my God, this amazing model's weights have been leaked on the internet or on BitTorrent or something, that's what's going on. Right? All these coefficients have been leaked. Because once you know what the coefficients are and what the architecture is, you can just reconstruct the model. All right, so that's what's going on here. Now, why did we do this network business? Why did we write it as a network? Yeah, what is the advantage? Any guesses?
Why would we write it as a network? What's the advantage? We have like interconnectivity.
When you have multiple functions from the network, so it's just easier to see it that way.
Right, if you have lots of things going on, it's easier to see it if you actually write it in graphical form. Yes, correct. But so is it only like a usability advantage?
The other thing is you want different functions for different layers of the.
OK. So maybe we want to use different functions in different layers. But I think there's actually even a larger, sort of a more basic point, which is that then the moment you write it down, you suddenly realize that I could have lots of things in the middle. I don't have to go from the input to the output directly. I could do lots of things in the middle, right? That's sort of the key idea. So what you do is, so remember the notion of learning representations of unstructured data.
Yeah.
Right? Where you take a picture and say beak length and things like that. Right? And remember, I said deep learning actually automatically learns these things. Where is that automatic learning coming from? Well, this is where it's coming from. So what we do is we take this thing, right? This is just a logistic regression model. Inputs get added up as a linear function, run through a sigmoid. And then we are like, if we want to learn representations of the raw input, we better be doing something in the middle here. Because the output is the output. That's not going to change. You know, it's either a dog or a cat. You don't have any choice as to what it is. Okay? The only agency you have at this point is you can take the raw input and do things in the middle with it.
Okay, yeah.
You can do a lot of stuff in the middle and then run it through something to get the output. Okay? So in any mathematical discipline, if someone comes to you and says, here's a bunch of data, I want you to do something with it, what is like the most basic first thing you should do?
Clean it, look at it.
Run it through a linear function. The most basic thing in math is a linear function. So given anything, just run it through a linear function, see what happens. So that's exactly what we can do. So the simplest thing we can do here, we can insert a bunch of linear functions. So we do is, we take all this input and we just run it, we do a linear function on it. So think of this as x1 times 2 plus x3 times 4 and all the way to xk times 9 plus some intercept.
I'm not even doing anything, it's just freezing. I don't know why.
We do a linear function on it. So think of this as x1 times 2 plus x3 times 4 and all the way to xk times 9 plus some intercept, and boom, it goes to the other end. So this little circle here with a plus in it is just, thank you. This is just a linear, it's a shorthand for a linear function. So whenever you see a circle with a plus, it's just a shorthand for a linear function. Okay? So you can take this whole thing and run through a linear function, and when you do it, you'll get some number right there. You'll get some number. So you have taken these k numbers and you have sort of compressed them in some way into one number. Okay? But you don't have to stop at one number. You can do more. So we can have a stack of linear functions in the middle. Right? There's a linear function here, another one here, another one here. At this point, the k numbers you have, k could be, for example, 1,000. Right? It's just the size of your input data. You have taken these k things and you have compressed them into 3 numbers at this point. Okay? So, okay, maybe 3 is the right number, maybe 10 is the right number, we don't know. And we'll get to, well, how do we know what the right number is later on? So we can stack as many linear functions as we want. So we have transformed this k thing into a 3-dimensional vector, right? K numbers become 3 numbers. And now we can flow these 3 numbers through some other little function. Okay? And as you will see in a few minutes, that function is called an activation function.
Yeah, ReLU,
and it's chosen to be a
sigmoid
nonlinear
squish.
function. Because if you don't choose it to be a nonlinear function, all the effort we are doing is
for
going
nothing.
to be a total waste of time.
Right, that just turns
Okay.
all into a linear
For now, just
transformation.
Take it
All
on
stacked
faith
on top of
that
one
you need to have
another.
nonlinear functions here. But note that
We need to
the
have
3 numbers
activation
here
at this layer
are still 3 numbers.
provide
They
some
are 3 different
separation.
numbers, but they're still 3 numbers. And once we do this,
In a
you'll be
way.
like, you know what? This was fun. Let's do it again. Okay? So you can do it again.
Hey, what's up, Tim?
And you can keep on doing it. You can keep it 100 times if you want. And the key thing is that every time you do it, you're giving this network some ability, some capacity to learn something interesting from the data,
Yeah.
to learn an interesting representation. Now, of course, you're thinking, well, how do we know it's interesting? How do we know it's a useful thing? And we'll come to all that later on. Right? We're just giving it the capacity, the potential to learn interesting things from the data. Whether it actually lives up to its potential, we don't know yet. Okay?
Yeah,
We'll give it
this
the
is all
potential.
lining up with what we've been learning
Because
so far.
the more transformations of the input data you make, the more opportunity you have to do interesting things with it. If I don't even give you the opportunity to transform it once, you don't have any opportunity, right? If I give you 10 chances to transform things, you have 10 shots at doing something useful. So you can do this repeatedly, and once we are done doing these transformations, we just pipe it through to our good old logistic regression sigmoid here, and we are done. Okay? So this is the basic idea. And so just to contrast it, this was good old logistic regression, where we take the input, we run it through a linear function and pop out a number, a probability number. But after we do all this stuff, the input stays the same, the output stays the same, but in the middle, you just run it through a whole bunch of these functions, these layers, boop, 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 and then we get the output. Okay? That's all we have done. And this is a neural network. A neural network is nothing more than repeatedly transformed inputs which are finally fed to a linear or logistic regression model. Any questions? Could you use the thing so that everyone can hear? Yeah.
Yeah, two questions. Firstly, so when we say that there is a challenge of explainability, is it that we don't know which arrow it went through? That's one. Second, who's controlling the number of iterations or the number of functions? That's up to us, or how does that work?
Right. So So the first question, explainability. We actually know exactly for any given input data point, we know exactly how it flows through the network. So there is no problem there. The problem is in ascribing, okay, we think this person is going to be repay the loan because of this particular attribute. We don't know that.
Doesn't make any sense. This thing is so stupid.
Repay the loan because of this particular attribute. We don't know that because those attributes all get enmeshed together and goes through this complicated thing. So we know exactly what happens. We just can't give credit to any one thing very easily. I'm just standing on the brink of this vast ocean of something called explainability and interpretability, which I'll get to a bit later on in the semester. But that's sort of the quick, kind of rightish, kind of wrong answer. Okay. Number two, we decide the number of layers. We decide a whole bunch of things. And as we'll see in a few minutes, there is something that's given to us and something we get to design. And I'll make it very clear which is which.
Okay. Good question.
Yeah. Did I say your name right?
Yeah. So which functions have to be linear, and also like why does it have to be linear?
Yeah. So these functions, the f of x here, they have to be nonlinear. As to why they have to be nonlinear, we'll get to that in a few minutes. Okay, so these are called neurons. Okay?
Yeah.
These things where basically there's a linear function followed by a little nonlinear function.
Functions at each
right?
layer.
This is each one of these things is called a neuron.
To distinctly transform
the way,
the layers and alter the data
this is
to get
loosely
unique representations in
by
between
the
each
way
layer.
how our neurons work in human
kind of like
mammalian
introducing
brains.
some like not
but
randomization,
the
but just
connections
some, like,
between neuroscience and deep
nudging.
learning are very heavily argued. So I'm going to like stay away from it. Okay? Suffice it to say, I just think for building practical deep learning systems in industry, you're not worry about this. Okay? All right, let's move on. Terminology, this vertical stack of linear functions or neurons, right? This vertical stack is called a layer. Right? This is a layer, that's a layer. And these little nonlinear functions, which we haven't gotten to yet, are called activation functions.
Sigmoid functions.
And we'll get to why they are called that in just a second. And
input layers, hidden layers, and output layers, right?
It's called an input layer. And I have the word layer in double quotes because like it's not really doing anything, right? It's just the input. So, but we call it an input layer. And what the very final thing that produces our output is called the output layer, right? Obviously, and everything in the middle is called a hidden layer. Okay? So the final piece of terminology is that when you have a layer like this, in which say 3 numbers are coming out, and there's another layer, right? If every neuron in this layer is connected to every neuron in this layer, it's called a fully connected or dense layer. So for instance here, this arrow that's whatever number is coming out, let's say the number 3 is coming out of this thing here, that number 3 flows on this arrow to this thing, flows on this arrow to this neuron, and flows on this third arrow to this neuron. That's what I mean. So every neuron, its output is being sent to every neuron in the following layer. Okay, we call it fully connected or dense. And then
That's what that means.
if you look at logistic regression, right, this is just logistic regression. You can see basically logistic regression is a neural network with no hidden layers. So in some sense, logistic regression is like almost the simplest possible network you can think of, like barely a neural network, right? It's got no hidden layers. That's what makes it logistic regression. And so, as you might have guessed by now, deep learning is just neural networks with lots and lots of
deep layers.
Of what? Yes, layers. So here are a few. And by the way, these are not even considered all that impressive these days. Okay, but I put them up because this thing here is called ResNet, and it's famous because the ResNet neural network was, I think, the first network to surpass human-level performance in image classification. It's sort of like the Skynet of image classification. Okay, it surpassed human-level performance. And I'm putting it up here because we'll actually work with ResNet on next Wednesday. And we'll actually take ResNet, we'll fine-tune it, and solve a real problem in class. All right, so it's got lots and lots of layers. Now let's turn to these activation functions. We have been ignoring these little guys, right, so far. So the activation function at a node is, first of all, it's a function that receives a single number and outputs a single number, right? It's not very complicated, right? It receives, basically, this is a linear function which receives all these inputs. It could be 10 inputs, 1,000 inputs, runs it through a linear function, outputs a number, and that single number, a scalar, goes in here, and it comes out.
I might have to. I gotta like restart the stream after this. This is just so annoying. Single number.
This is a linear function.
I should not be running out of RAM. I've got 38 gigs of RAM. Like, it's not. I don't know what it is.
Which receives all these inputs. It could be 10 inputs, 1,000 inputs, runs it through a linear function, outputs a number, and that single number, a scalar, goes in here, and it comes out as another single number. Just remember that. And so these are some of the most common activation functions. In fact, the sigmoid we saw, which is actually be used for the output, is actually a kind of activation function where a single number comes in and it gets mapped into this curve because of this thing. So the single number that comes in is a, and it gets transformed as 1 divided by 1 plus e raised to minus a, and you get a shape like this, and this is called the sigmoid activation function. And as you can see here, for very small values, for very negative values, it's going to be pretty close to 0, meaning it won't get activated. And for very, very large values, it's going to be pretty close to 1. All the action happens in the middle. When your values are somewhere in this range, there's a dramatic increases in what comes out.
Yeah,
okay?
so it like basically
that little thing in the middle is the sweet spot.
Dramatizes the weight, in terms of its perspective.
I'm almost embarrassed to call it an activation function because it's literally not doing anything. It's sort of getting a nice label for free, right? It says you just get a number, you just pass it straight along. It's a linear activation function, but just for completeness, I want to put it here. And then we come to the hero of deep learning, which is the rectified linear unit, right? Rectified linear unit. It's called ReLU, and ReLU is going to become part of your vocabulary very, very quickly. And so ReLU is actually a very interesting function. So you write it as maximum of whatever number and 0, which is another way of saying if the number is positive, just send it along unchanged. If the number is negative,
make it 0.
Send a 0 instead. Squash it to 0. So which means if the number is negative, nothing happens. If the number is positive, it wakes up. So what happens is that you could have a very complicated linear function with millions of variables, and then it puts a single number, and that number unfortunately happens to be negative. The ReLU is not impressed. It's going to send a 0 out.
Yeah.
Okay? It's a very simple function. And
that
many,
helps solidify
many
what that
folks
is.
who've been
That
in
makes
deep learning
sense.
for a long, long time believe that the use of the ReLUs is one of the key factors that led to the amazing success of deep learning, because it's got some very interesting properties, which we'll get to hopefully on Wednesday. OK, so the shorthand here is that whenever you see this thing, it's just a linear activation, linear function followed by just sending it straight out. If you do this, if I put a ReLU in here, I'm going to denote it like that, which mimics the graph, how it looks. And if I put a sigmoid, I'm just going to use this thing here. OK?
Gotcha. Okay.
Just a visual shorthand. There are many other functions, activation functions, by the way. There's something called the tanh function, the leaky ReLU, the GeLU, the swish. I mean, it's like a menagerie of activation functions, because very often researchers will be like, well, I don't like this activation function. Here's a little modified version of the function, which is going to be better for certain things. So, people's research creativity is sort of, at this point, has gone unhinged. So lots of options. But if you just stick to the ReLU for your hidden layers,
this guy's good. I
you
like
can
him.
basically get anything done practically, right? You don't have to worry about anything else. So we'll only focus on ReLUs for all the intermediate stuff. Yeah.
Yeah, how do you gauge which activation function is more suited for your use case?
Yeah, so the rule of thumb here is that for your hidden layers, use ReLUs, right? Because empirically, we have seen that they do an amazing job. For your output layer, your very final thing, you actually don't have a choice, because what you have to use depends on what kind of output you have to work with. If it's an output which is a probability number between 0 and 1, you have to use a sigmoid.
Okay.
If it is, say, 10 numbers, all of which have to be probabilities, and they have to add up to 1, you got to use something called the softmax, which we'll get to on Wednesday. So it really depends on the output, and the nature of the output dictates what you use in the output layer.
The finalized function, the loss function, right?
So
that's what he's talking about.
Coming back to this, so if you want to design a deep neural network, the input is the input, the output is the output, and so you get to choose everything else. You get to choose the number of hidden layers, the number of neurons in each layer, the activation functions you're going to use.
So dumb.
The input is the input, the output is the output, and so you get to choose everything else. You get to choose the number of hidden layers, the number of neurons in each layer, the activation functions you're going to use, and for the hidden layers, and then you have to make sure that what you choose with the output layer matches the kind of output you want to generate. Okay, so this is all in your hands. You decide what happens, but there's a lot of guidance for how to do these things, which we'll cover as we go along. Did you have a question?
Kind of, but I guess I'll do it. Is there also exploration in kind of dynamic setting of layers so that our user is predetermining the amount of layers, but the system itself is finding its own layers?
Yeah, so there is a whole field called neural architecture search, NAS, where we can actually try a whole bunch of different architectures and then use some optimization and, in fact, reinforcement learning, which we won't get to in this class, as a way to figure out really good architectures for any particular problem. But
that makes sense, right?
The question of, OK, when I'm training a model with a particular kind of data, the first pass through the training data, I'm going to use 2 layers. The second pass, I'm going to do 7 layers. That is not done. And the reason it's not done is because of certain other constraints we have and how we can do the optimization and the gradient descent and stuff like that. But what you can do, and we'll look at this thing called dropout. For certain layers, you can actually, for each time you run it through the network, you can decide in this layer, I'm not going to use all the nodes. I'm going to drop out a few of the nodes randomly. And it's a very effective technique to prevent overfitting, and we'll come to that a little later.
Cool.
Yeah.
One question regarding neural networks is about the coefficients. Is the system going to decide its define on its own, or we have to use it as a
It's so research intensive and
no, the whole trick
developing
here, the whole name of the game is
just
we
tons of
use
new
the
ideas
data,
coming out.
the training data, and something called a loss function, which I'll get to on Wednesday, along with an optimization algorithm, so that the network figures out by itself what the weights need to be, what the coefficients need to be, so as to minimize prediction error.
Yeah,
we talked about that's the whole thing. The magic here is that we don't have to do anything. We only have to set it up, sit back, often for many hours, and watch it do its thing.
Just one last question. You mentioned nodes just now when you were answering Rolando's question. Can you just confirm exactly what a node is? I have an idea that it's basically any circle, but you've just added a lot more detail.
Sure. No, when I'm referring to a node, I'm literally referring to something like this, which think of it as a linear function followed by a nonlinear activation. So it receives a bunch of inputs, runs it through a linear function, and passes it through like a ReLU or a sigmoid or something, and out pops a number. So in general, a node will have many numbers potentially coming in, but only one number going out. Now, that one number may get copied to every node in the next layer, but what comes out of that particular node is just a single number. All right, so let's use a DNN for our interview example. So in this problem, we had two inputs, right? GPA and experience. Yep. The output variable has to be between 0 and 1 because we're trying to predict the probability that someone gets called for an interview.
Yep.
So the output size is fixed. The input size is fixed. The output is fixed. So since it's really only the very first network we're actually playing with, let's just start simple, right? We'll just have one hidden layer, and we'll have 3 neurons, right? And as I mentioned to Tommaso's question from before, if you are choosing activation functions in the hidden layers, just go with the ReLU as a default. It usually works really well out of the box. So we'll just use a ReLU. And since the output has to be between 0 and 1, we don't have a choice. We have to use a sigmoid for the output layer. OK? That's it. So we have those are our design choices. And when we do that, this is how it's looked like, right? We have 2 inputs, x1 and x2, GPA and experience. And then it goes through these 3 ReLUs. And then out comes these 3 numbers. And they pass through a sigmoid, and we get a probability y at the end. All right, quick question, concept check. How many weights, how many parameters, both weights and biases, does this network have? Just take a moment to count.
Does it show it? How many weights and biases does this have? Okay. So that's our question here that we're trying to solve, is how many parameters, weights, and biases does this network have? Well, we know that we are feeding 2 parameters into every node, into every linear function, right? And at each node instance, you're adding a bias to that. Now, the question is does the bias, is there a bias for each of those circles, or is there one bias that's being applied at each of those circles, right? That's the thing, is there a distinct bias or at each circle, or is it just one bias at the node layer, like a global bias that's being applied?
Inputs x1 and all right, any guesses? Yeah?
Sure.
I think you're almost there. Are folks going to be doing binary search on this now? Okay. No. Yes?
13.
Yes, very good. So that's 13. And my guess is that the reason you came up with 12, and I made the same mistake, that's why I know it, is you probably forgot this green thing here.
Okay, got you. So, okay, got you, okay. So I wanted it as like in total rather than the whole network. So you would have parameter 1, 2, 3, 4, 5, 6, right? These are, individual input. These are your input layers, right? And these are the, these are the 3 values in the vector at each layer, right? So 3, 6, we have linear functions and activations happening at the hidden layer, right? So biases would be applied at each of these. So 7, 8, 9. And then you have 10, 11, 12, 13. Okay.
What folks often forget is the bias, right? We all count the things, right? Okay. And the easy way to do it is, okay, 2 things here, 3 things here, 2 times 6, 3 is 6, 3 times 1 is 3, another 9, and then you have to add up all the intercepts, right? So you get 13. And so when we get to very complicated networks, the first 2 or 3 times you work with very complex networks, and we'll do it starting very soon, just get into the habit of hand calculating the number of parameters, just to make sure you understand what's going on. Once you get it right a couple of times, you don't have to do it anymore. Okay? The first couple of times, hand calculate to make sure you get it. Okay, so yeah, so let's say that we have trained this network using techniques which we'll cover on Wednesday, and it comes back to you after training and says, okay, these are the optimal, the best values for the weights and the biases.
The red are the weights and the green
so now
are the
your
biases.
network is ready for action. It's ready to be used.
Right, so we have 9
so,
weights.
So what you can do is, let's say that you want to
biases.
predict with this network, if you have x1 and x2, what comes out of this top neuron, right? Let's call it A1. It's basically this. Okay, that's what's coming out of this thing. For any x1 and x2, this is what's coming out. Similarly for A2 and A3.
Right, you're doing the linear function,
and then what comes out at the very end
part,
is,
and then you're taking the ReLU, right?
A1
that max,
that,
0, or that linear
plus
function.
A3 times
It's just
that,
nested it together.
Plus 0.05, and the whole thing gets run through the sigmoid, and that's what you get. Okay? So this slide and the one before, just make sure you look at it afterwards and to make sure you totally understand the mechanics of it.
That makes sense.
Because
I got it.
This is really important. If you don't fully understand, like internalize the mechanics, when we get to things like transformers, it's going to get hard. Okay, so just make sure it's like automatic at this point. It should be reflexive. Okay, so yeah, and so when we want to predict anything, just run some numbers through it to get all these things. And boom, we calculate it. Turns out it's 22.6. That's the answer.
Those result in new outputs
or
new
so,
representations.
I just want to say that let's say that you built this network, and now you're like, hey, given any x1 and x2, I can come up with a y, but I'm feeling a little mathy. Can we actually write down the function? Yeah, you can write down the function. This is what it looks like. Super interpretable, right? So this goes to the comment that Ita, you made earlier on, where the act of depicting something using this sort of graphical layout makes it so much easier to reason with and to think about compared to trying to figure out what this function is doing.
Yeah.
Right?
Agreed.
The other point I want to make is that just contrast what we just saw with the logistic regression thing we saw earlier, which was this little function. And so here, even this simple network with just 3 hidden layers, 3 nodes in that single hidden layer, right? It's so much more complicated than the logistic regression model. So much more complicated, right? Mm-hmm. And it is from this complexity springs the ability of these networks to do basically magical things. Right? That's where the complexity comes from. That's where the magic comes from. So, and here in this case, the number of variables hasn't even changed. It's still only 2. But we can go from the 2 inputs to the 1 output in very complicated ways, as long as we know how to train these networks the right way. That's sort of the secret sauce, which we'll spend a lot of time on. So yeah, to summarize, this is what we have. It's a deep neural network. By the way, this kind of network where things just flow from left to right is called a feed-forward neural network, in contrast to some other kinds of networks called recurrent networks, which we won't get to in this class, because transformers have in this class, because transformers have actually proven to be much more capable than recurrent networks, and those have become the norm, so we'll just focus on those instead. And so this arrangement of neurons into layers and activation functions and all that stuff, this is called the architecture of the neural network. And as you will see later on, the transformer, the famous transformer network, is just an example of a particular neural network architecture, much like convolutional neural networks, which we'll get to next week for computer vision, or another example of a particular network of an architecture. So we will focus on transformers. They are a particular kind of architecture. All right, so in summary, that's what we have. You get to choose the hidden layers, the neurons, activation functions, stuff like that.
Yeah.
The inputs and the outputs are what you have to work with. And so we will actually take this idea and then use it to actually solve a problem from start to finish on Wednesday.
Cool.
So I think I'm done. I give you 3 minutes back of your day. Thank you.
Nice. That was good. Have you tried using Claude Code to take notes? No. I don't need AI to take my notes. I think at that point, it's gone too far. Okay. I don't need to offload my learning onto AI. It's so funny. Okay. Cool. That was a great lecture. That was actually super, super awesome. I'm really sorry for the frequent pausing that took place with the glitching. I'm really not sure what's going on. I probably just have to restart my laptop. I don't know, something's going on with the encoding or whatnot of the stream. So, anywho, but that was a really intuitive, that was stream. So let's just do a quick little recap then. Right, so we first talked about traditional AI, how the goals with traditional AI were to kind of map all of the rules, kind of sitting down with industry experts for every single scenario. Think of like old school kind of chess bots or things like that, how if you had this scenario on the board, you play this move, right? Now think about, well, that has some limitations and some bottlenecks we can already think of right off the jump. You know, if we add in, let's say we have a new version of chess, a new 2026 version that adds in a new piece. Well, now we have to go back into our giant rule set and update how that new piece interacts with every single other rule, and then implement another set of rules on top of everything for specifics of that piece. So it's just a huge overhaul of additional implementation and whatnot. So that's why we kind of moved into machine learning. Now, machine learning is where we take input and output examples and find ways to define those rules using the computer without having to, set them up ourselves. So we can take input examples through the means of structured data, right? Converting, real world examples or things that you see in the real world, or even computer examples, into data that the computer can actually read and interpret. And so we can feed these into machine learning algorithms and models and functions. So what we get at with that is where you feed into input layer into various things, linear regression models, neural networks, gradient boosted machines, all these different types of concepts and mathematical techniques for machine learning, in order to predict, generate rules, so that when on training data and testing data, so then when you have a solidified model, if you then feed it additional non-testing data, non-training data, but actual like real world data, you can have like it's trained on things, right? It's been trained on certain inputs, certain testing data. So if you give it data that corresponds to some of the similar to the test, you could probably get like real world answers. So let's say you're testing on the NIST data set, just the handwritten digits or whatever, and then you actually start feeding in your own handwritten digits on your trained model and see how well it performs against your handwriting or whatever like that, right? So that's where that is. And then it talked about structured versus unstructured data, right? So the computer, when using machine learning, needs a way to be actual to interpret that data. It can't just be kind of noise. Like you think about how images, videos, whatever. There are data underlying in terms of like the pixel values and sizing. There is data corresponding to that, but there's no context behind that. Remember how we talked about how a singular blue image or pixel on a screen, his jacket, this blue is part of his shirt. Well, this blue could very well have been part of his jacket. We didn't know that, right? So, or the computer doesn't know that. We just know that because our brain right now is seeing this and interpreting, knowing our past training data that we grew up on and whatever, that this is a shirt and that the contrast difference at this edge makes up his jacket, right? We're able to kind of interpret that with our brain. And so that kind of leads back to what that bottleneck of traditional AI is, that we have our brain, the way it does things is different than the way we kind of verbally communicate them. And so that's where we get into deep learning. So deep learning actually is a way to take and handle the unstructured data, right? Rather than having to spend years and a bunch of money and time, gathering, researching polling individuals, sampling a bunch of data, finding accurate data sources and whatnot to train deep learning, to train machine learning models on. There's this concept of what deep learning is, right? There's another inner subset of machine learning, to where you can feed it unstructured data and it can try to figure it out on its own and do that kind of, that cleaning through various mechanisms of, forward propagation, back propagation, gradient descent, stochastic gradient descent through batching of the data, all that kind of jazz. And we're going to get into that into future lectures here. We're a little bit ahead of this lecture as we're using these lectures to solidify our knowledge. We're first going through and reading the texts and then watching some solidified YouTube videos to help, and then we're going through and then watching the lecture, right? So this is a pretty good, actually, kind of a study mechanism if you're in college to use. So you don't want the first time you're coming into the lecture to be your first exposure. That really will bottleneck your learning ability in the lecture, and you'll have to go back and spend a lot of time catching up. You want the lecture to be kind of like a refresh or a review on the material so that you're able to kind of be the one answering and asking questions and using this time with the professor to solidify the knowledge rather than just first learning it for the first time. If you're able to do that, I guarantee you will be successful in college. It's a pretty it's a known hack, but it's not a lot of people take advantage of it. It does require you, though. You have to, put in an hour and a half or two before class to go over that material and really try to understand it in your own way, and whatnot. But so that's what we got into deep learning, right? You feeding in that unstructured data, and yes, this does require a lot more like computationally expensive as you're trying to, do a lot more maybe calculations and back propagation and whatnot, trying to fine tune these weights and do that kind of a supervised learning on your data. And the thing is then we get into the next case of generative AI, right? Where generative AI is the ability to create unstructured data on its own rather than having to be fed unstructured data, right? Or be trained on any unstructured data. It's actually able to create its own and kind of its own, think about its own personality or in its own perception. It's kind of crazy to think about, right? And then we just got into like just the basics about what is a neural network, right? And this was a very good review about neural networks, and it was solidified a lot of things regarding that. So thank you guys so much for hanging out with me. I would love to learn machine learning, but I'm not very good at math. Is there a way to still do it or get into it? I'm not very good at math either. I've taken calculus back in college and some advanced statistics classes, but that was a long time ago. So it's all pretty vague. I haven't actually implemented that in a long time, and I think that honestly, I think that the math barrier is a little bit overplayed than people like to. The math, the notation is what scares a lot of people, I think, but the actual what's going on in the math, if you really think about it, is I might be naive, but from what I've seen and stuff, it's really easy to interpret the math and just kind of basic Python for loops, and summations. It's if you have the ability to kind of read Python functions, it makes the notation of math a little bit easier, in my opinion. Right? But I will say exactly as Wawa said, is that if you're not wanting to know the math, like if you don't have like a desire or a passion, like an interest, we'll say, like if it doesn't spark your interest, then honestly, I don't think that maybe it's like necessarily for you in terms of like a passion. Like, why are you wasting your time really if you don't really care about the inner workings of what's going on? Like, yeah, I mean, you might be able to get some results, but you're going to be fairly abstracted away of understanding what's going on behind the scenes. And at that point, you might kind of have like imposter syndrome, at least personally, from a professional standpoint. If I'm going to claim to want to implement these in the real world, and I kind of want to know what I'm talking about, and I don't want to, it's kind of like an ethical thing as well, right? So that's kind of interesting. Math is actually a big barrier. yeah. It's definitely hard stuff, right? I think we have a little bit of a lucky scenario because we're just doing it for fun. So it's not like we have tests or anything that have put a lot of pressure on it. We're kind of able to just move at our own pace. I'm going to sign off on the YouTube video. I'm not going to go anywhere on the stream, though. I kind of want to sit and answer some questions and talk. It seems like there's a lot of people that have questions. We have a lot of new people in on the stream and a lot of new people that joined the channel lately. So, but I'm going to sign off on just the recording here because I'm going to upload it back. All right, you guys, this was... hold on, let me quickly. Let me just go up to the front here. Let's just go back to the start. Oh, see, it's really being annoying. I don't know why it's doing this. All right, you guys, this is Hands-On Deep Learning, 15773, Spring 2024 of MIT. Lecture 1, Introduction to Neural Networks and Deep Learning, Training Deep Neural Networks. This was a really awesome lecture. I'm really excited to keep going on this one. Thanks so much for being here, and I'll see you guys in Lecture 2. All right, that's enough for the recording. That one's going to be a pain to edit. All of those breaks I'm going to have to find. I was really hoping. What's really nice about the lectures is that I kind of just sit there and watch, and I kind of pause every 15 minutes for a couple of minutes. So it's really easy just to break those out. But with the random jumps that it's going to have, it's going to be really annoying to go through. Ugh, whatever. I'll try to get chapter 2. I'll try to get chapter 2 up for you guys soon as well of the deep learning. That one's going to be a pain to edit as well. So for those that are new here, my name is Michael. Welcome in. I've got a degree in human biology and a minor in chemistry. I work as a biologist or biochemist or whatever. I currently do have a job in a lab. I've been teaching myself how to program for a little over a year and a half, 2 years almost now. About 2 years now, pretty much. Kind of crazy. We built some cool projects. If you guys haven't seen our Polyworld project, I'll pull that up. Go ahead and check it out. We built a full stack app live on stream using React and Python. Come on, let's go. Right, so you can, this is Polyworld. It uses the Polymarket APIs, and we have a custom kind of statistic engine generating a leaderboard based on a more optimized leaderboard based on the current leaders of Polymarket. And then you can actually go on to these individual snapshots that are refreshed every 12 hours and get some more information about their edge, open positions, overall prediction accuracy, and overall, statistical analysis. So it's a pretty cool program, or a pretty cool site. Honestly, I think it's kind of underrated for what it gives you. It gives you some pretty cool traders that you can kind of look up here and see. We track appearances as also as streaks. So that's another cool little feature that we implemented. So make sure you guys go check it out. You can also do searches. If you make an account, you can do better searches and save custom snapshots to your account, which is pretty cool. We implemented like bcrypt and hopefully some proper user authentication and things like that. Trying to learn how to do all that, cookies, all that jazz. So pretty cool project, polyworld.app. If you guys, oh shoot, it's not showing. This is like really annoying. Like I really don't know what's going on. I'm gonna have to stop the stream. Polyworld.app. Sorry, you guys. Right. Anyways. Yeah, I'm gonna have to restart the stream. I was gonna try to go longer here and keep going. Maybe do. I'm gonna take a break. I'm gonna come back in about 2 hours, and we're gonna do some C programming. We're gonna keep going and try to finish up the exercises from chapter 13, and then maybe move on to chapter 14. But thanks so much for being here, you guys. This was a great stream going over and doing this hands-on deep learning. I'm actually surprisingly surprised. I'm surprisingly surprised about how much I'm actually understanding now. How much we'll be able to implement, that's another story. But I'm really proud that I've actually been able to separate out this information. We've been reading the book. We took our time through those chapters. We took solid notes. We reviewed those notes. I watched additional YouTube videos on the subject, on the introductions and the inner workings. We watched the MIT. So we're really getting a lot of base exposure to we're hitting a lot of the same points over and over again, but it's really solidifying a strong base. So as we build, we're not going back and having to remember things and struggle with filling in gaps. That's something that's been a trend on this channel that I've been trying to, that's I think has been successful with our learning, is that I've been really taking our time on the basics and on the fundamentals, so that when we go into more advanced topics, like right now I'm not having to go back and learn Python and figure out Python. Like imagine trying to do this, like you're in school and you barely know how to code in Python. Like, and he's showing you Python examples, and you vibe coded your way through your Python courses, and now you're on deep learning in your master's program, and you are trying to also watch Python courses. There's just not enough time in the day, right? And then you have another course, you have labs that you have to teach, you have all these other things. So, that's where the college people the struggle is with college. Is the compounding of material, and then the gaps that don't get filled as things continue to compound. So here on this channel, we don't have that. We can just kind of chill and just really grind out at our own pace. So what's going on? Does anybody have any questions or anything? Let me get caught up on some chats. What's going on, Casper? Hey, Insomniac. Engineer Muhammad, what's going on? JSNA Fawns. Wow, what's going on, Tim? The Punisher. Yeah, we'll probably watch the next lecture maybe tomorrow, maybe tonight. Who knows? I've been really actually motivated to learn this stuff. It's been pretty fun to really smash my head against a wall and force myself to learn hard things here. But, okay. That's all. Then I think I'm going to head out for right now. I'll be back in a few hours where we'll continue on and do some C programming and stuff. So, see you guys then. Peace out.